Okay, so thanks everyone for coming. My name is Daniel Kelly. I'm a second year PhD student at NUI Galway under the supervision of Dr. Enda Barrett and Dr. Frank Glavin. So today I'm going to talk to you about the work we've carried out recently on potentially a looming form of cyber attack that targets functions as a service applications known as denial of wallet. So just a quick overview of what serverless computing or functions as a service is. Serverless computing is a cloud computing execution model in which the cloud provider allocates machine resources on demand, taking care of servers on behalf of their customers. Serverless computing does not hold resources in volatile memory. Computing is rather done in short bursts with the results persisted to storage. When an app is not in use, there is no computing resources allocated to the app. Pricing is based on the actual amount of resources consumed by an application. As such, serverless aims to provide pay-as-you-go event-driven functionality. So applications are developed as per each desired process and the event that invokes it. So serverless function platforms provide the infrastructure to deploy code for execution across their cloud and define the event processing logic that prompts the function to run using the model event, trigger, and action. So serverless applications are highly scalable as functions are executed in containers across the provider's cloud infrastructure. Serverless is a misnomer in the sense that servers are still used by the cloud service providers to execute code for developers. However, developers of serverless applications are not concerned with capacity planning, configuration, management, maintenance, fault tolerance, or scaling of containers, VMs, or physical servers. Therefore, there's no need for a dedicated team to manage software in-house, sparking the term no ops or no operations. Serverless computing abstracts back-end management from users, allowing only minimal access to some basic parameters, such as function memory allocation and function runtime timeout. Serverless functions can simplify the process of deploying code into production. Serverless code can be used in conjunction with code developed in traditional styles, such as microservices or monoliths. Alternatively, applications could be written to be purely serverless and use no provision servers at all, although this shouldn't be confused with, for example, peer-to-peer computing. So the four largest commercial offerings are AWS Lambda, Google Cloud Functions, IBM Cloud Functions, and Microsoft Azure Functions. And some popular open source offerings are Kubeless, Fission, OpenFaaS, and OpenWhisk. So defining denial of wallet, we define denial of wallet attacks as the intentional mass and continual invocation of serverless functions resulting in financial exhaustion of the victim in the form of inflated usage bills. Execution costs are increased via excessive function runtime, invocation count, and additional resource consumption. This is achieved by exploiting the massive capability for scaling, as the platform will handle the increased load, but will incur costs in doing so. A denial of wallet attack is a form of attack that particularly affects serverless computing. Given the scaling capabilities of serverless platforms, as a result of being hosted on a vast cloud of virtual machines, the effects of a regular denial of service attack can be dealt with by massively scaling to handle the volume of requests. However, the scaling comes at a price, as function as a service bills the application owner per runtime of each function invocation. This resulting volume of function invocations following a denial of service attack would therefore incur financial exhaustion of the application owner. As such, the term denial of wallet came to describe this attack, since unlike denial of service, where the service is targeted and disrupted, the wallets or the finances are the target of a denial of wallet. The result is an application owner who must now pay for function executions that are not in fact legitimate usage. So one of the earliest uses of the phrase in a publication is in the Open Web Application Security Projects, or OWASP's, report on the security risks of serverless computing in 2017. It's mentioned as a risk to consider along with traditional denial of service attacks. Prior to this, denial of wallet was often referred to as financial exhaustion attack, denial of capital, or simply serverless denial of service. However, we believe that a serverless denial of service attack and a denial of wallet attack can be seen as independent threats, with the former focusing on maybe serverless specific resource exhaustion, and the latter being as we've described. And it's probably worth noting as well that denial of wallet, I believe the term was coined on Twitter kind of as a joke, people theorizing the most expensive VM instances, for example, you could provision on some cloud provider. So the mechanism of attack, as mentioned in our definition, denial of wallet could be seen as the result of executing a denial of service attack on a serverless application. So this would equate to maybe an HTTP flooding attack on an exposed API endpoint that serves as a function trigger. However, any web application firewall will allow you to impose rate limiting on requests from a particular source. And also, serverless platforms allow you to set up billing alerts such that you can disable an endpoint in the event of an unusual spike in costs. So such an attempt at causing denial of wallet could be trivial to protect against, although it's worth noting that if you don't protect against it, it certainly is an issue. If you don't impose that rate limiting, it can go up quite quick. As such, we've theorized a potential mechanism that attackers could use in lieu of that. So we've termed this mechanism a leech attack. So taking example from slow rate denial of service attacks, such as Slowlaris or Are You Dead Yet? A leech is a malicious program that continually triggers API endpoints that invoke functions. The leeches operate indefinitely and at a rate that would not be detected by reasonable web application firewall rate limiting. So the key difference between denial of wallet on serverless applications and denial of service is that denial of wallet does not need to execute all at once to consume all available resources to cause damage. As such, a leech denial of wallet attack could be executed over a long time span and potentially even appear as legitimate traffic. So the leech can, of course, be of a distributed nature. The more leeches triggering API endpoints, the higher the bill will be. And unless you have some reason to believe that this is illegitimate traffic, then it'll go unnoticed and the bill will be paid. As such, boiling the frog would be an apt analogy for this form of attack. So you're slowly increasing the heat such that the victim doesn't notice the danger until it's too late. In denial of service mitigation systems that use, say, an adaptive rule set, so can change the firewall rules based on fluctuation in this deemed to be real traffic, a denial of wallet attack can again utilize the fact that it can be executed over a long time span. So unlike a rigid firewall rule where it'll be forever limited, if the attacker gently increases the intensity in such a way that the mitigation system adapts to it, it could then establish new false normative baselines. So as well as API triggers, serverless functions can also be invoked through, say, uploading to a storage service, such as S3 buckets on AWS Lambda. So this introduces maybe the concept of a serverless specific attack pattern, such as function input parameter exploitation. So for example, one could trigger a function that uploads to a storage service with images of the largest size that incurs the greatest runtime possible of the function execution. So as in you keep increasing the size of the image that you're uploading until you reach some function timeout or file size timeout, then use that as the basis of your attack going forward. So use that largest size of image as your attack parameter going forward, so you incur the greatest runtime, therefore the highest bill. So to fully realize the potential harm a denial of wallet attack may be capable of, it should not simply be seen as a slow burning denial of service attack. Instead, it would fully exploit any oversights the developer may have made. If there is no limit imposed upon functions that process files, the runtime of a function will increase. Or if there is no rate limiting on function invocation, continuous streams of requests may come in. So future work on denial of wallet detection may potentially have more in common with fake traffic and social media bot detection rather than denial of service in its pure form. Although as the term denial of wallet is already the established term for this kind of attack, it'll certainly evoke thoughts of large-scale flooding with immediate ramifications. And while this is not impossible, in our opinion, it could be this leech variant of denial of wallet that may pose the greater risk. So scenarios and motives for denial of wallet attacks. So motivations for attacks like denial of service will be are largely the same as denial of wallet. Some interested party wishes to cause a disruption to a victim's service as a form of revenge, ransom, threat, retaliation, or just simply a desire to cause chaos. Denial of wallet is different in this regard, however, due to our theorized maybe leech and deceptive attack methods like that function parameter exploitation. We believe that the motivations to cause such damage are slightly more nuanced. We akin the motivation to perform a denial of wallet over a denial of service on a victim to that maybe of espionage or sabotage. So one party wishes to covertly affect another in a negative way, thus giving the attacking party the upper hand when, say, a critical matter arises. So one scenario we theorize that best exemplifies that this is that of a party wishing to stifle the growth of a startup company. So a startup company offers some service powered by serverless computing. This service has potential to pull clientele from the attacking party. The attacking party may then initiate a denial of wallet leech that will gradually ramp up fictitious usage on the startup service. And this will drive up the startup service usage bill for no tangible return, unbeknownst to them. The startup will continue to pay for their serverless platform and may also invest in other areas given their newfound usage. And then the attacker may then cease the denial of wallet, reducing the startup's usage to a much lower level, and that does not justify the capital invested. The startup finds themselves in a precarious position where they've spent a large amount of their budget on the serverless platform's bills and may have taken, maybe loans backed by their previous success. That just simply doesn't exist anymore because it was all illegitimate. So this could cause the stifling or even the shutdown of that startup. So this example could be applied to any situation where a smaller entity is vulnerable to their serverless powered service being targeted for denial of wallet. Given that the attack's most powerful trait is the ability to go unnoticed, it could be used as a tool for maybe even larger politically interested entities to silence or weaken any opposition. For example, finances spent on inflated serverless bills is money not spent on organizing demonstrations or anything like that. Now, a common use case of serverless functions is in applications is an image reprocessing, such as creating a thumbnail from a user uploaded image. So we ran some tests using AWS Lambda as an example to demonstrate how one could exploit input parameters. So I briefly introduced this concept when going over the mechanism of attack. We created a function that resizes images to 128 by 128 pixels for use as a thumbnail that is triggered by a user uploading an image to an S3 bucket. We allocated 512 megabytes of memory to the function, and we found that because we found that this was the lower limit required to handle the largest images we were uploading. So the thumbnail is uploaded after it's been processed, is uploaded to an S3 bucket, and images of increasing size were uploaded, and we observed the effect on function runtime. So unsurprisingly, there's an increase in runtime with an increase of image size. In this scenario, it would fall on the developer to impose a hard limit on image size. However, for example, as smartphones are producing higher resolution images with each new flagship device, the baseline of an acceptable maximum image size gets pushed higher and higher. So this makes even a well thought out function susceptible to input exploitation. So as a reference, an Apple iPhone X takes photos producing an image of 4032 by 3024 pixels, and cross-referencing our prior experiments on input exploitation, we can take a rough runtime of say 2,950 milliseconds with our memory allocation of 512 megabytes as a benchmark for a potentially legitimate function that a malicious user would consider targeting for a denial of wallet attack. We can then conduct a cost analysis of this function on the 4 largest commercial serverless platforms: AWS Lambda, Google Cloud, Microsoft Azure, and IBM Cloud functions, for increasing number of function invocations using a serverless function cost calculator we devised in order to compare the bills of these 4 platforms in given scenarios. So this calculator, it just takes the number of function requests, the runtime of each of those functions, and the memory allocation of the functions as inputs, and returns the total cost of executing those functions, inclusive of all free allowances granted by each platform and additional costs such as API call costs in accordance to the official guides on the pricing of each platform. So with a modest botnet of 1,000 nodes, a slow rate attack of 2,000 requests per hour will cost an application owner roughly $40,000 after 1 month, and between 400,000 and 500,000 if left unchecked for a year. So these figures are certainly outlandish, and it could be argued that such costs would be noticed. However, it's worth noting that this is an example of a very unsophisticated attack to demonstrate that costs can indeed add up on these serverless deployments. And it would be on the attackers to devise more sophisticated methods of kind of staying under the radar with their attacks. So detection and mitigation. To date, there is little or no targeted research on any denial of wallet. We believe this is due to an absence of publicly known occurrences of attacks. This poses a unique opportunity to be ahead of the attackers by mitigating against attack methods that are early in development. The vulnerability exists in serverless technology, and it probably would be naive to believe that it would not be exploited. Research on denial of wallet will encompass strategically approaching the issue from the perspective of a bad actor. And it's kind of an example of preemptive cybersecurity investigation. The domain shares many key attributes with bot detection, denial of service mitigation, and just cloud security in general. So that does mean it inherits their pitfalls and difficulties as well. So this research aims to bring a dormant threat that is in the conscience of the community and potentially address it before it may even begin to develop. And we can, come up with effective mitigation strategies before it can become a prominent threat. So going forward, we'll be looking into, the application of machine learning on detection of this attack, potentially by using graph-based detection approaches, as such approaches have worked with good success in, say, social media bot detection. So a number of questions has arisen in the process of our investigations on denial of wallet. Firstly, is denial of wallet unique to serverless computing? So take, for example, an application that utilizes elastically load balanced VMs for computation. This indeed could suffer a denial of wallet in the event of a large flooding attack, forcing the system to scale up. Another example would be flooding a storage service with data. If that storage service scales upwards to accommodate the increased load, it too will incur higher usage costs. These two examples show that the term denial of wallet can indeed apply to other scenarios than serverless. However, we certainly feel that the leech variant of denial of wallet is indeed unique to serverless computing. A denial of wallet on serverless need not be the result of a flooding attack like in previous examples. Therefore, we feel that future research on denial of wallet in general should also acknowledge these other scenarios. So next, is denial of wallet even possible given the safety measures a developer can use to secure their applications? So these safety measures, among others, are rate limiting and billing alerts. Like I said previously, so rate limiting will indeed protect against these flooding attacks. However, as we've discussed, they could be overcome by doing a slower attack. So the leech. Billing alerts at the end of the day require a human to decide whether to take the service down or not. So obviously that is the most effective strategy to mitigate a denial of wallet. However, the issue arises in the detection of the attack in the first place. If the developer isn't inclined to believe that the usage is illegitimate, they may continue to let the service run. Also, regardless whether they let it continue or not, if the billing alert has been met, then that's a bill that's going to have to be paid. So if you're continuously hitting people's billing alerts, it's not only is it, money for nothing, but it's frustrating as well, just constantly getting this illegitimate traffic. And lastly, is it economical to launch a denial of wallet over some other form of attack, or can a leech even cause enough damage? So the value associated with denial of wallet attack can be tricky to estimate. As I mentioned in the motives for a denial of wallet attack, the end goal may not necessarily be an all-out financial ruin of the victim. So we don't believe it to be as simple as it costs $10 to cause $7 worth of damage. Therefore, why would I bother with the attack? So in the scenario I previously described, if we have a large entity that is the attacker, and they say they pay $1,000 a month to cause, that will cause $700 a month of damage to some startup company with that has some enterprising serverless application, that 700 excuse me, that $700 less they can put into further development. So it goes to the running costs, and also $700 of perceived usage. So they think that they've had this big influx in usage on their apps. They go, fantastic, maybe we should invest in furthering our application. So now the startup has maybe hired new developers, given the recent success, and then the attacker stops their leech, and all of a sudden the startup's application usage plummets. And this leaves the startup, like I said, in that position where, they're suddenly down in traffic. They've paid all this money immediately because of the pricing model of serverless. And even though the larger entity may have paid more, it was worth it to them in the long run because their competition is now crippled. So from this initial investigation on the emerging threat of denial of wallet attacks, we've concluded that there is potential for significant financial damage should a malicious entity wish to exploit the unique selling points of serverless computing. Future work on the mitigation of such attacks will need to tackle the following concerns: future research on fictitious request classification, securing serverless applications from our proposed threat of leeches, further investigations into unique weaknesses of serverless computing for novel attacks, and the detection of fake users and mitigation of their actions. Meaningful data must be generated in the absence of historical attacks, rather than wait for a large-scale attack to occur. So the barrier to obtaining such data is the creation of realistic test rigs that can be put under various attack simulations without actually incurring real-world financial damage. Because obviously, if you're denial of walleting yourself, there'll be no money left to do any more research. So we conclude that effective denial of wallet attacks will certainly be of a distributed nature. A single source really is not capable of delivering severe damage in realistic scenarios where proper security procedures have been followed. It is then in conjunction with existing and future distributed denial of service research that distributed denial of wallet will be investigated. So we propose that denial of wallet attacks are potentially one of the latest threats in cybersecurity. With the ever increasing adoption of serverless computing, it's a threat that really should be considered. Our work has provided a baseline for further research to be carried out in the field. Our simple attacks incurred theoretical damage of significant value. And while these numbers seem outlandish, it is an important baseline for a worst case scenario that could be built upon to prevent such attacks becoming a reality. So thank you very much for listening. I welcome any questions you may have.
Thanks amazing, Daniel. So just to summarize quickly, Daniel is a second-year PhD student of mine and Frank's. He's been working on this probably about a year and a half. The first 6 months, he was targeting a different area, but then when COVID hit, he had to pivot into this domain. I spotted, before I continue, I spotted a quick question there. John Barry, I think, has posed it there. If you want to address it, Daniel. So do authentication and authorization of the API requests have a role to play in mitigating these attacks, in addition to the mitigations outlined?
Yes, so I briefly touched on fake users as a potential realm that would need to be investigated for these attacks. So if you had, a number of fake users that could bypass this authentication authorization of the API requests, then it can continue to allow those requests to go through. Because like I said, it doesn't have to be an all-out flood. If you had, say, 1,000 fake users that could get past this authorization, then you could potentially start to invoke the APIs that they have access to, thus upping the invocation count.
Yeah, Sybil attacks.
Yeah, exactly.
Known as Sybils, yeah. Tell me, is there anyone out there using serverless or thinking about using it? Anyone know what it is even? It'd be interesting to, anyone want their application attacked or are happy to allow it to be attacked for the purposes of our research?
That's what I was going to ask. Where do you go with this? Daniel's a really fascinating project and very, very novel and original. And I googled leech attack, right, but it comes up as something meaning something completely different in a not security context. I suppose coming from my background in the School of Business and Economics and College of Law, I suppose College of Business and Law, you were talking about aspects there that straight away I was thinking, are there legal precautions here? It may be worth talking to Ronan Kennedy, for example, in the School of Law on that to see about the efficacy of legal protections. And of course, the law is only the law, and it can be very easy to work around it. You talked about factors there which are very much the economics of cybercrime as well towards the end, and of course there's some work being done in that space, talking about the rational actor, I suppose, and the rationale for actually doing this. Now they would just be, I suppose, an aside to kind of your main work. What you have demonstrated is that this threat can happen. Whether people choose to invoke it or not, I mean, I don't think that's really maybe a bit out of scope for your project. I mean, going towards economics and law things, you've demonstrated that this actually is a real attack. Whether it makes sense or not, that's a different matter. But how you actually research this, and I was waiting for your detection and mitigation. I was waiting on that to see what you're going to say. Mm-hmm. Does benchmarking come into it? I mean, in terms of, is there a responsibility here for the service provider to say, actually, well, for other organizations of similar scale and size who have similar services, what we're seeing happening to you is a bit out of kilter. Is there a role for that in terms of, does the service provider have a responsibility to detect fraud and to prevent fraud? And actually, it would be interesting talking to Ronan Kennedy about that from the point of view of contractual matters, in terms of if fraud is going on here, who actually is to blame for it, and who ultimately takes the hit on this, because then that pushes you back to who takes responsibility for ensuring that appropriate measures are in place to prevent it, be that in criminal law or be that in civil law. For example, was the service provider negligent in not being able to detect, you say, extraordinary behavior? So that's the most interesting part of all, is how you're going to detect this, and even the mitigation, I think, may be beyond the scope of your PhD. But if you were able to come up with algorithms that could actually detect this actually happening, I think that in itself would be a really, really valuable contribution. And there's plenty then for future work down the line.
That's, sorry to cut in, that's certainly the hope going forward now. I briefly mentioned one of the biggest barriers to this research, especially on the detection side, is the lack of data, that there are no known historical attacks. So what we're having to do is develop these simulators, essentially, that allow us to attack ourselves without incurring real money, but we have to accurately cost what those attacks actually are valued at. So that's currently what we're doing now. And we're trying to build these data sets of potential attack vectors, these slow rates, even some flooding ones as well, just to be totally sure. But obviously, with denial of service, where you can test it by actually just destroying some system that you've rigged up in isolation. It's not as easy with serverless, because all the open source versions of serverless, there's no costing involved in that, of course, and it's never going to be as scalable as the commercial offerings. So then when you're testing the kind of the flooding style of it, is it even is it value? So certainly these are all the difficulties, and these are what we're going headfirst into right now. What you said about the legal side of it, is the onus on the provider to know, like, oh, if this was fraudulent, don't worry, you don't have to pay it. And this is certainly outside the scope of where I exist in computer science, but I fully acknowledge that this attack is almost more of a like a financial economic attack than it is a technology-based attack.
Yeah.
And saying that, where stuff like this has happened in the past, small scale, for example, where just hobbyist developers have left an API endpoint out to be hit, and they have been hit with potentially an attempted denial of service rather than a targeted denial of wallet. They did have to pay the bill in the end. They could flag it with the provider, but in the end, they're like, no, too bad. It was your fault for not setting it up right. You pay the bill. And there was even a case, I believe it was last year. It was the Dallas Police Department, I believe. They started a service where people could upload videos of crimes being committed during the BLM protests, and it ended up being targeted with a flooding attack. Everyone uploading these K-pop videos, and they had no limits put on their storage service, and usage just went through the roof, essentially, with all these videos being uploaded, large videos. And allegedly, now obviously no one from the police department would come out and say how much they had to spend, but allegedly they had quite a large bill to pay to Amazon, and Amazon were like, no, this is usage, you didn't set it up right, you have to pay. So it's all kind of almost anecdotal in terms of like who has to pay, who's at fault, all this sort of thing. But I would like to see, like you're saying, going forward, the legal aspect of this kind of crime. Could something be put in place to protect people from honestly a simple mistake? If you didn't put in the correct rate limit, or you left something open, or there was some kind of loop even in your services that kept triggering itself over and over and over again. So that's definitely an avenue that I will certainly have to go down, to not so much justify, but to just give good example that the attack it's not entirely reliant on the technology of serverless itself. As I discussed, it could be any price per whatever costing platform. It is just, where does it stop? It's like, say you have a $5,000 bill after leaving something running overnight without you realizing, and it was hit, who's at fault here, kind of thing. It's a really tricky one, and it is early days. Like I said, there's little to no academic research on this kind of thing, so we're very much venturing into new territory here.
Michael Schukat looks like he wants to say something.
How do you know? Daniel, well done. This was a cool presentation. I liked your slides, really well done. I have another question for you, and John already mentioned the authentication of API requests, which basically would boil down that you have a kind of a client-side authentication before you actually, can do an API call. Well, in this case, down the road, I suppose you could look into user profiling as well. Basically, how many requests, in average, are there any peaks or troughs? So which in a way would bring you straight into kind of the area of machine learning, distinguishing between what is deemed a normal usage pattern and a non-normal, which is, I suppose, application specific, user specific, etc., etc. And I'm just wondering, do you have any thoughts on this, how kind of machine learning could be kind of incorporated into your research?
Yes, I hope so. So I mentioned briefly like a graph-based approach. So in social media bot detection, one way they've done that is they create these graphs of connections between these users, these Sybils. And let's just say, Sybil A is friends with Sybil B and C and D on Facebook or whatever, and they all happen to be, posting the same kind of stuff. By constructing these graphs, you could potentially sort of like create this network of vastly different people, that should really not be connected to each other, because they are just pure random bots that have been created. So what we might be able to do is create graphs of incoming traffic, where let's just say maybe it's silly enough to continuously use the same IP addresses from the botnet or whatever that's attacking, and they all happen to come in at the same time or together or do similar style of requests. So you've got a big block of requests that might be similar to each other. Could we use some algorithm to classify kind of these fictitious blocks based on potentially graphs created from connections to an application as a whole, or even individual serverless functions? So that is, like I said, that's the next step. So what we're doing currently is like I said, we're trying to create these attack vectors. And I mentioned previously, we have to think from the perspective of a bad actor. We kind of almost have to come up with the attacks ourselves. What do we think would be good enough to cause damage, but also go under the radar? And then once we've sort of theorized, not totally flushed them out, because that would be a bit evil, flushed out these attacks, where can we go from there in terms of detecting them, and can that be applied to slight variations in it later down the line, hopefully.
Great, thanks.
Really interesting. So John Paul Meany has a question there. So John is saying, well, the victim changing a micropayment for using their service as a possible deterrent.
I like that. That's good. Certainly, like there are, as was mentioned, even with the authorization on the API request, all those sort of things. Those are the recommended best practices for securing your applications. However, these best practices were written kind of to deal with denial of service style flooding attacks. And we will do more research into the flooding style of denial of audit, because obviously that's where the big bucks come in. You start seeing bills in the thousands potentially if it's not secured. But when it comes to the slow rate attacks, like they will be a bit less brute force kind of thing. So if there was an application that was doing such a thing, like charging a micropayment for each service, it probably won't be attacked. So the attackers will be, or could be, looking for the easy way in first of all. Like I said, we have to think from the perspective of the bad actor, but at the same time, we don't want to, go too in depth with designing overly sophisticated attacks, I suppose. But obviously, yeah, these are good ways to mitigate, at least from the worst case attacks that could happen. Well, I like that question. Sorry if you don't mind me jumping in. So as Enda said, slightly jokingly, but also quite seriously, if anyone did have a serverless deployment that would be happy for us to attack, that would be great. But no, joking aside, that is the hard part. So we'll have to model serverless applications. If someone already had one in deployment, not so much that we'd attack it, but even if we got, say, baseline usage statistics off of it that we could use as in like a workload generator as the actual traffic, and then we could put our attack on top of that. That's what immediately springs to mind, because there is so little data on this kind of thing. And obviously as well, serverless architecture is, it's new. I mean, what, 2015 is when it really started taking off. So people are still adopting it, and maybe they're only using it as a single part of their application, and maybe that's all you need. But we do want to approach this from the point of view of as many cost per action services in an application as possible, I suppose. So to wrap up what I was saying, we just need more exposure, I suppose, to serverless applications and potentially how they operate behind the scenes. Otherwise, we're just going to have to keep, for example, looking at, I believe it's AWS offer very good overviews of architecture of example applications, stuff like that. We would just have to recreate those in our simulations and go off good reckoned figures of usage, that sort of thing. But if we had access to a real world deployment, wouldn't that be great? That'd be fantastic.
Yeah, by all means. Don't all rush at once. Just to go back to one other point that Michael raised with regard to Ronan Kennedy. Now, Ronan, for anyone that doesn't know, is in the School of Law here in Inyo Galway. And prior to publishing this, I had contacted Ronan to ask him for advice on that, legal advice as to, I suppose, culpability. So would we be liable if someone took this exploit and went and ran with it? Because let's be honest, Daniel's paper is basically a how-to instruction on how to perform this attack. He wouldn't put anything down over email, and he told me to contact a solicitor, which I didn't do. So is there anyone out there on the call that can offer guidance? If you'd find or discover some vulnerability, or you're researching some new attack and you develop a really, really good way of attacking a system, can you publish it safely?
I would say yes, and I mean, because in a sense, what you're doing is you're highlighting a vulnerability. I mean, and there are lots of reward packages out there for exactly this type of thing, and maybe that's in fact what are they called? Those what are they called? But there are packages out there that are specifically inviting people to identify these vulnerabilities, identify attacks. So what you're simply doing is highlighting here is a vulnerability. I would see no, I mean, and okay, right, I'm not a solicitor on it, but from the point of view of a researcher, that's all that you're actually doing. You're highlighting you're not committing the act. You're bringing it to the attention of security people that this is something that you're potentially open to, and now you need to be able to defend and mitigate against that, and that's the real challenge. But I wouldn't see that ever as an issue that if somebody brings to the attention of the community that there's a vulnerability that could be exposed, that they will be anyway liable for like a how-to guide and how to do it. Because if you don't figure it out, the cyber criminals are, and you can be sure as hell they aren't going to publish it.
That's for sure.
So in terms of the underlying motive here, that's what it comes back to.
It does,
is not to gain from it, but rather to share the details of the vulnerability with the community, to highlight it and say, look, what can we do to circumvent this? And it's interesting. I was also thinking about things like say salami slicing, which goes way back, which I suppose was also that idea of the slow burner, that thing that went unnoticed for many, many years, but eventually it is kind of picked up as being an abnormal activity. And that may well be it. And go back to Michael's point about machine learning. It may well be just that you're using analytics to detect abnormal activity, using benchmarks and guidelines and authentication and whatever else we can figure out, graph networks and whatever else we can.
I suppose if you took, let's say, an e-commerce application and you saw that 500 items were added to a cart within a very short time period, maybe a couple of seconds, I think you could pretty much say that that's not a person doing that, and I think there's ways and means of doing that kind of analysis. Dynamic Bayesian networks, these kind of things could work very well. But anyway, look at that's for another day. Another thing I just wanted to bring up as well, that my second-year undergrads pushed some code up onto GitHub before, which contained their keys for AWS. And I think Bitminer was deployed in one of their VMs and ran up a couple of thousand euros worth of bills. But in fairness to Amazon, they waived it. So maybe it's because they were students, I don't know, and they're undergrads, but that's something anyway. But I think if you're a private company and you deploy, I think you're in trouble. You should have your own developers that are checking into this. And I think I don't think they'll waive the cost there, Anyway. I don't know if that's basically it. Oh yeah, bug bounty hunting. Yeah. I thought that's what you were referring to, but I didn't want to.
Yeah, that was it. That was it. Yeah.
I was going to shout when I said no. Okay, well, I think we're probably getting close to the end. I'd say. I know it's a pretty short call, I assume anyway. And I think there's no more questions, is there? Caroline was just saying thanks to Daniel. Very well presented. So yeah, I think we can all agree. Very well done. And is this the first of these, Michael? I'm sure it is.
I think we're wrapping up for the summer with Cyber Tuesday, so we're back again in September. But but this event is recorded, so I think today perhaps doesn't suit everybody, Daniel, to have attended. But I think what you've done is you put yourself